Hello and welcome to Integrated CMOS Non-Reciprocal Components for Full-Duplex and 5G millimeter wave applications with Professor Harish Krishnaswamy. I'm Mike Hamilton, your host for this IEEE Microwave Theory and Technique Society webcast, which is sponsored by the MTTS Education Committee. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We'll send all registrants an email when the archive webinar goes up so you can revisit it or share it with your colleagues. Second, we encourage questions. We'll answer them after the talk, but you can submit them at any time during the discussion. Enter your question in the Q&A box in the webcast window, and don't forget to click Submit. Third, some words about the interface. You can enlarge slides by clicking on the rectangle at the top right of the live slide window. You can also enter full screen mode if you desire. Refresh or reload the current web page if you encounter any problems. With regards to audio, if you're listening over your computer speakers, you can adjust the media player volume. You may also need to adjust your system's master volume. Also, the icons at the bottom of the webinar window include a resource list. Clicking that link will start the process to download copies of the slides that will be presented today. Now let's introduce our speaker. Professor Harish Krishnaswamy received the Bachelor of Technology degree in Electrical Engineering from IIT Madras in 2001, and the MS and PhD degrees in Electrical Engineering from the University of Southern California in 2003 and 2009, respectively. In 2009, he joined the Electrical Engineering Department at Columbia University in New York, where he is currently an associate professor and director of the Cosmic Laboratory. In 2017, he co-founded Mixcom, a venture-backed startup to commercialize Cosmic Laboratory's advanced wireless research. His current research interests include integrated devices, circuits, and systems for a variety of RF millimeter wave and sub-millimeter wave applications. Professor Krishnaswamy is a recipient of numerous awards. He's been a member of the Technical Program Committee of multiple conferences, currently serves as Distinguished Lecturer for the IEEE Solid State Circuit Society, and as a member of the DARPA Microelectronics Exploratory Council. So now it's my pleasure to turn the virtual podium over to Professor Krishnaswamy for integrated CMOS non-reciprocal components for full-duplex and 5G millimeter wave applications. Harish?
Thanks, Mike. So this is the so I'm happy for it's a pleasure for me to present this webinar today. I'll be talking about my work on non-reciprocal components in CMOS for full-duplex and 5G millimeter wave. This is the outline of the presentation. So I'll start with an introduction to non-reciprocity, and then I'll talk about the first work that we did in this space that uses a circuit called an N-path filter to demonstrate a non-reciprocal circulator. Then I'll talk a little bit about our work in pushing this up into the millimeter waves using a switched transmission line architecture for circulators. And then I'll spend some time talking about recent advances that we've made after these initial two works, where we've been pushing these circulators to higher performance, as well as incorporating them in larger systems for applications such as full duplex. And then I'll conclude this presentation with a brief discussion on future research topics in this space. So what is reciprocity? So reciprocity is a very fundamental precept of electromagnetics that we see every day in our life. So reciprocity loosely states that waves have to propagate in the same manner in forward and reverse directions. And it's basically why if you have a speaker that's emitting some sound and you're listening to that from some distance, if you interchange the position of the speaker and yourself, you still hear the same sound, the same volume of sound, etc. And similarly, if you look at optics, if you have a ray that's traveling from one medium to another, if you reverse the direction, the ray will travel in the same manner in which it came. And this concept of reciprocity, that waves must travel in the same manner in forward and reverse directions, has many implications in science and engineering. And in our field of microwave engineering, I'm pointing out two implications of this. So it is reciprocity that states that if you have an antenna, then its radiation pattern is the same as its receiving pattern. It transmits and receives in the same manner. Similarly, reciprocity is why a power splitter also functions as a power combiner if we look at propagation in the reverse direction. The concept of reciprocity is a very deep one, and it spans many bodies of physics, and it has a very rich history. So all the way back in the 1820s, Green formulated the first reciprocity theorem for electrostatics. Then if we move forward into the 1840s, we saw the Stokes-Helmholtz principle of reversibility in optics, which is essentially intimately linked to reciprocity. And then Helmholtz came up with the formulation for reciprocity in acoustic systems in the mid-1850s. And then Rayleigh wrote down the reciprocity relations for motion in dynamical systems in the 1870s. And in the 1890s, Lorentz wrote down the reciprocity theorem for electromagnetics in the form in which we use it today, which is shown on this slide. And similarly, you had reciprocity relations for thermodynamics in the 1930s, which won the Nobel Prize for in chemistry. And in the 1940s, Telegen proposed the first non-reciprocal component. He proposed a component called a gyrator, which violates reciprocity. The two-port equations for the gyrator are shown in the slide, where the relationship in the forward direction and the reverse direction are exactly the same in magnitude, but have a 180 degrees phase difference. This component, the gyrator, was postulated by Telegen as the fifth elemental circuit component beyond the resistor, the inductor, the capacitor, and the transformer. And essentially, with the gyrator and the four other reciprocal components, any arbitrary non-reciprocal network can be synthesized. And shortly after the proposal of the gyrator, the first microwave gyrator was actually built in the 1950s. This was at Bell Labs using magnetic materials. So with that history of reciprocity in mind, non-reciprocal components are used widely today in many different applications. And one sort of emerging application of non-reciprocal components is shown on this slide, namely full-duplex wireless communications. So all of today's communications are half-duplex. They're either separated in time, which is called time division duplex, or in frequency, which is called frequency division duplex. But if you could transmit and receive at the same time, at the same frequency, an operation which is called full duplex, you have the potential to immediately double network capacity in the physical layer while offering many other benefits at the higher layers of the network. So full duplex is an exciting new wireless communication paradigm, but there are several challenges associated with it. If you're transmitting at the same time as you're receiving and at the same frequency, then the receiver has to operate in the presence of a very large amount of interference from the transmitter. This transmitter self-interference, as it's called, can be more than 100 dB more powerful than the signal that's being received. And the non-reciprocal circulator is an important piece of this, as it allows the transmitter and the receiver to interface with a shared antenna while offering isolation between the transmitter and the receiver. So part of this 100 dB of self-interference suppression or isolation can be obtained from a component known as a circulator, which is a non-reciprocal component. So why is non-reciprocity important for that particular operation? So if you look at a three-port network that would interface a transmitter and a receiver to a shared antenna, if the three-port network is reciprocal, then fundamentally there has to be at least 3 dB loss between the transmitter and the antenna and the receiver. And so using a reciprocal network, and an example of a reciprocal network that's shown on this slide is the electrical balance duplexer. So using a reciprocal network as the antenna interface for a full duplex application means that you have to take in at least 3 dB loss on the transmitter and the receiver side. And so non-reciprocal circulators are useful in that they can allow you to avoid this fundamental 3 dB loss. So fundamentally, any linear time-invariant passive system built using conventional materials is reciprocal. And so this immediately points you towards the ways in which reciprocity can be broken and non-reciprocal components such as circulators can be built. So you can use unconventional materials, namely ferrite materials, which under a biasing magnetic field lose their reciprocity and can be used to build circulators. And this is the dominant way in which all non-reciprocal components such as circulators and isolators are built today. The challenge, though, is that these types of materials are not compatible with semiconductor IC fabrication processes, and so they tend to be external components that are connectorized and hence are bulky and expensive. You can use nonlinearity to realize non-reciprocity, and this is an approach that's widely used in the optical domain. However, in microwave applications such as communications, it's very important for the system to be linear. And these nonlinear non-reciprocal components such as isolators and circulators exhibit their non-reciprocity only over a limited range of signal powers. You can use active devices. Any active amplifier device is inherently non-reciprocal. It has gain in the forward direction, but has isolation in the reverse direction. But any active transistor adds noise and adds nonlinear distortion to the circuit, and so to the system. And so circulators and isolators that have historically been built using active devices such as CMOS transistors or BJT devices typically have poor linearity and noise performance, and they're not suitable to be used at the front end of a radio frequency transceiver, for instance. And so this brings us to the final method to break reciprocity, which is to use time-variant systems, to break the time-invariant necessary condition for reciprocity. And so this is a research direction which, again, has a long history, but in recent times has really seen some important advances. And why this direction of research is exciting is that fundamentally time-modulated or time-variant systems can be theoretically noise-free and distortion-free. And so it is possible, at least theoretically, to build very high-performance non-reciprocal components using time variance. So with that introduction, let me talk about our first work in this space, the N-path filter-based non-reciprocal circulator. So in order to understand how this circuit works, let's take a look at how non-reciprocity is generated in ferrite materials. So if you take a ferrite material, a magnetic material, in general, in the absence of a magnetic field, all the magnetic dipoles are misaligned. But if you apply a biasing magnetic field, then all the magnetic dipoles align along that biasing magnetic field, and now a wave that propagates along this magnetic material will exhibit non-reciprocal wave propagation. So when it travels in the same direction as the biasing magnetic field, it will experience a twist in its polarization vector in one direction, while it will experience the opposite twist in the polarization vector when it travels opposite to the direction of the biasing magnetic field. And so this non-reciprocity is what's used to build non-reciprocal components such as circulators and isolators. And this method of operation in ferrites is interesting because it sort of sheds light on what you fundamentally need to achieve non-reciprocity. To achieve non-reciprocity, you need some way of providing a bias or a preferential direction of propagation for waves in that medium. And here that's being provided by the magnetic field. But there are other ways that you can provide this bias, and there's been work on modulating the permittivity of a medium to provide a bias for the traveling wave. And so there's an example on the left-hand side of the slide from UCLA, where along a transmission line, capacitors are modulated with a traveling wave. And so now, along the original transmission line, if you have a wave that's propagating in the same direction as the modulating wave, then it will pass through. With a frequency shift, as is shown here, where the incoming frequency is shifted up and down by the modulation frequency, while a wave that's traveling in the opposite direction passes through the transmission line unchanged. And so now the direction of propagation of the wave has been converted into a frequency difference, and you can use duplexer filters to now separate the forward and reverse traveling waves. On the right-hand side is another method, again, employing the modulation of permittivity or capacitance from circuit sense. This is work out of UT Austin, where, again, capacitors are modulated, but this time not along a traveling wave transmission line, but along a resonant ring. And when this is done, if the modulation is propagating clockwise, then there is a preference for signals that also propagate clockwise along the ring. So signals can propagate from port 3 to port 1 and from port 1 to port 2 and port 2 to port 3, but not in the reverse direction. And so now we've essentially realized circulation in a ring, or essentially a circulator as a non-reciprocal component. And the advantage of this approach is that the non-reciprocity is achieved without creating a frequency shift in the signal that is actually propagating. So these initial works were certainly exciting, but one challenge in translating these works into an integrated circuit implementation is that permittivity is a hard parameter to modulate. On an integrated circuit substrate, for instance, in silicon and CMOS, varactors can only change their capacitance by a ratio of roughly 2 to 4. And so there's an interest in finding ways to create non-reciprocity without having to modulate varactors or permittivity. The insight that we had was that in a semiconductor substrate, conductivity is a parameter that can be modulated over orders of magnitude range. If I take a transistor switch, the resistance of that switch can change by up to 5 orders of magnitude when I turn the transistor on and off. And that's fundamentally what a semiconductor can do well. It can change its resistance or its conductance based on a gate bias over orders of magnitude. And so we started to look into how I can use switch-based circuits to create non-reciprocity. And so the first work that we did in this space is shown on this slide in a sort of a cartoon representation. So if you look on the right-hand side, imagine a switch that is rotating across a bank of 4 media, for instance, and on the other side as well, there's a switch that's rotating across those 4 branches. But now consider the situation where there's a phase shift between the switch on the left and the switch on the right. So if you look at this figure very closely, the switch on the right is sort of leading in phase by 90 degrees. So now if you imagine the signal propagating through this structure, it's sort of getting a twist towards the counterclockwise sense when it travels left to right. But when it travels from right to left, it is sort of getting a twist in the clockwise sense. So this phase shift between the switches is providing a non-reciprocal twist to the signal. And the idea is to sort of mimic the twisting of the signal that happens in ferrite materials under the application of an external magnetic field. And so here, what happens is when the signal travels from left to right, it picks up a phase advance of 90 degrees, while when it travels from right to left, it picks up a phase lag of 90 degrees. And so there's a non-reciprocal phase shift that is created in this circuit. So how this would be realized in an electronic circuit as opposed to that mechanical example is one would have these switches that are switching across some bank of 4 or more media. And in our first case, we actually used capacitors. So you imagine switches, capacitors, and switches, and these switches are being switched at an RF rate. But what we now have is that there's a phase shift of 90 degrees between the switches on the left and the switches on the right. Now, this switched capacitor circuit without the phase shift is actually a very popular circuit that has been extensively investigated over the last 7 or 8 years or so in the IEC community. It's commonly called an NPAT filter. And this circuit in and of itself is very interesting because when you look at the transfer function, it synthesizes a second-order LC bandpass filter response, but without actually using any inductors, just using switches and capacitors. But what we see here is with the phase shift to the clocks, in the forward direction, you still see that second-order bandpass response, but you create a phase shift in the phase response, while in the reverse direction, you have the same magnitude response as before, but you have the opposite phase shift in the phase response. And so you've created a non-reciprocal phase shift, as it were. So you can analyze this circuit. It's a little cumbersome for these linear, periodically time-varying circuits, as they are called, but it is doable. And when you analyze the circuit, and if you assume that there's a large number of paths in parallel, here I'm obviously showing only 4, but if you assume large number of paths, what you find is that this circuit ends up with the S parameters that are shown here, where it's perfectly matched at both ports. The forward and reverse transmission has unity transmission magnitude, meaning no loss, but there is a positive and negative phase shift in both directions, meaning you now have an ideal non-reciprocal phase shifter. And when this non-reciprocal phase shift is 90 degrees, if I use 90 degrees, then you have essentially a 180 degrees phase shift between the forward and reverse direction, meaning this has essentially realized Teligent's gyrator. This is the first realization of Teligent's gyrator on chip without using magnetic materials. So with this gyrator, obviously, as I mentioned before, you can build any kind of non-reciprocal circuit or network, we used a particular architecture to realize the circulator, which is shown on this slide. Namely, we wrapped a 3 lambda by 4 transmission line around this non-reciprocal gyrator. So what happens here is if you imagine a wave that's propagating clockwise as is shown, it starts at one end, rotates through the ring and gets to the other end, and in doing so, it will pick up a minus 270-degree phase shift from the line. Then it picks up a minus 90-degree phase shift from the gyrator, and so you have 360-degree phase shift, meaning the wave ends up at the same phase at which it started, and so clockwise wave propagation would be supported. But if we look in the reverse direction, the signal would pick up minus 270 degrees from the line, but plus 90 degrees from the gyrator, and so that's 180 degrees. And so when it ends up back where it started, it's actually 180 degrees out of phase from where it started, meaning counterclockwise wave propagation would be suppressed. And so essentially we've now created a ring where signals can only propagate in one sense, meaning we have realized a circulator. So, to practically realize a circulator, you actually have to add 3 ports to it, and it turns out that you can add these 3 ports anywhere along the ring as long as they are lambda by 4 separated from each other. Once you do that, you can calculate the S parameters of the structure using regular microwave network analysis, and it turns out to have the ideal S parameters of a circulator. So we built this circuit in a CMOS chip where the gyrator was realized on chip in a 65-nanometer CMOS process, and the transmission lines around the gyrator were miniaturized using L's and C's, with those 3 inductors being off-chip air core coil-craft inductors. And so this was the first CMOS non-magnetic circulator implemented in a chip, this slide is kind of showing the implementation. You can see that because of the fact that we're able to build it on a chip, and because the circuit in and of itself is deeply sub-wavelength, it is much smaller than commercial circulators that are currently available. That being said, of course, this was the first work, and the linearity of the circulator is way below what can be available, what is available commercially. Magnetic circulators, fried circulators can easily handle tens of watts of power and even more. And this first work was certainly quite limited in its power handling, but it represented a first advance that showed that actually building circulators on chip without magnetic materials is actually possible. So here were some measured results from this circulator, and the interested parties can certainly go and take a look at the paper to see additional results. We were able to achieve low loss of around 1.7 dB and very high isolation in the reverse direction, in excess of 50 dB at a particular point. And over a wide bandwidth, the 20 dB isolation bandwidth was something like 4% of the center frequency, which is around 750 megahertz. So that was our first work. Again, you could take a look at the papers to look at additional measurements. There are measurements on things like noise figure and P1dB and IIP3 and so forth. But after this work, we started to ask ourselves, is it possible to actually scale this approach up into the millimeter waves? And the challenge with these NPAT filters is that they require many clocks that are operating in square wave fashion at the frequency of operation. You need multiple phases of the clock that are square wave-like at the frequency of operation. And that's obviously very challenging to do at millimeter wave. So we started to look at another architecture where instead of switching across capacitors, we started to switch across transmission lines. And intuitively, the reason why this works up at higher frequencies is at higher frequencies, the clocks are running faster, and so you need to sort of delay the signal as it propagates through the gyrator so that when it gets to the other end, the clock has also been able to update to its phase shift. So in some sense, this delay that we're inserting between the switches as opposed to the capacitors that we had before intuitively makes sense. So this is what the structure looks like. It has what's called a Gilbert quad set of It has a Gilbert quad set of switches on the left-hand side, where in half of the clock, the signals are propagated in straight fashion, and in the second half, the signals are actually swapped in polarity using these cross-coupled transistors. Then you have a transmission line that has certain delay. And on the other end, you have another Gilbert quad set. But this set of switches is driven by a clock that is 90 degrees phase shifted from the set on the left. And the delay of the transmission line is also equal to this 90 degree phase shift. So let's see how the circuit works. So in the first half of the clock, the signal, if we're looking from left to right, will enter the line. It'll pass through the delay. Then when it gets to the other end, because there's a 90 degree phase shift in the clock, the straight switches are on again, so it just exits the line. And when we look at the second half of the clock, the signal goes through the crisscrossed switches, then passes through the line and incurs the delay. And again, because this delay is exactly equal to the delay in the clocks, when it gets to the other end, again, the crisscross switches are active and the signal comes out. So in the first half, you essentially pick up the delay of the line and nothing else. In the second half, you pick up the delay of the line, but these two additional sign flips, and -1 times -1 is obviously equal to +1, and so these sign flips cancel each other out. And so in both halves of the clock, in the forward direction, the transfer function is just equal to the delay of the transmission line, which is Tm over 4. But when we look at the reverse direction, in the first half of the clock, the signal enters through the straight switches, then it passes through the line. But now, because the switches on the left are leading the switches on the right, when it gets to the other end, the crisscross switches are on, and so the signal takes the sign flip and it comes out. And when you look at the second half period, first you enter with the sign flip, then you incur the delay of the line, and then when you get to the other end, the straight switches are on because these switches are leading compared to the right-hand side, and so you come out with no sign flip. So now in the reverse direction, you can clearly see that you pick up the delay of the line, but an extra sign flip in both halves of the clock. So there's an extra negative sign, which means that when I write the S parameters for this circuit, it's certainly matched at both ports. Transmission in forward and reverse directions is lossless. There's a delay, but there's an extra negative sign for reverse traveling waves. And so this extra negative sign is the non-reciprocal phase that we're trying to create. And the critical thing is that in this entire description, at no point did one assume that the frequency of the signal traveling forward and reverse is in any way related to the clock frequency. And so what I just said is true for any frequency of signal passing through the structure. And so essentially, this non-reciprocal phase shift is seen over infinite bandwidth. So this essentially is Telegen's gyrator because it has a 180 degree phase shift between forward and reverse direction, but it has operation over infinite bandwidth, theoretically infinite bandwidth. Now, of course, practically speaking, these switches will have some parasitics. There are limits to how fast they can be switched. The transmission line will have some dispersion. So, of course, there will be practical limitations to the bandwidth of this gyrator, but from an ideal sense, it is infinitely broadband. So now with this gyrator, we built a circulator, and pretty much in the same manner as before, where we wrapped a 3 lambda by 4 ring around the gyrator. And so once again, wave propagation is supported in the clockwise direction, but is prevented in the counterclockwise direction. So you again realize a circulator. And so with this idea, we built a circulator operating at millimeter wave at 25 gigahertz in 45 nanometer SOI CMOS. But the critical thing that enabled us to use this at high frequencies is because the gyrator is broadband, the operating frequency, namely 25 gigahertz, does not have to be linked to the clocking frequency. And so we were able to build a circulator working at 25 gigahertz, but the clocks are running at around 8 gigahertz, essentially at a lower RF frequency at which it is actually feasible to run these Gilbert quad switches. So this was the first millimeter wave passive non-reciprocal circulator without using magnetic materials implemented in 45 nanometer SOI CMOS. And again, you can take a look at the published papers on this to get some more information about the performance. I'll just summarize some of the performance here, where we measured around 3.2 and 3.3 dB loss in transmitter to antenna and antenna to receiver paths. But critically, the insertion, the bandwidth is much wider. The 1 dB insertion loss bandwidth is as wide as 4.6 gigahertz, which is almost 20%. And the reason for this wide bandwidth is the broadband nature of the gyrator within the circulator. So these were our two initial works in this space. The first showed that it's possible to build circulators on chip with a switched capacitor circuit, and the second showed how you could translate that idea to higher frequencies using switching across transmission lines. Since this work, we've made several new generations of circulators with improved performance. This is work that we did under the DARPA SPAR program shown here, where the same switched transmission line architecture is used, but now not at millimeter wave frequencies, but rather at an RF frequency of 1 gigahertz. But what going back down to low frequencies allows one to do is now the switches can operate at a much lower frequency than 1 gigahertz, so they were clocked at around 300 megahertz, which now allows us to use high power handling devices. So this circulator was built in 180 nanometer SOI CMOS, and we use the thick oxide devices in that technology to enhance the power handling of the circulator. And so we were able to realize a circulator that can handle in excess of 1 watt of power at the transmitter port with more than plus 50 dBm transmitted antenna IIP3. The other interesting feature in this work is we added some tuning capacitors that allow us to get maximum isolation even when the antenna impedance changes. So one of the problems with circulators in general, nothing specific to these time-modulated circulators, is that if the antenna impedance changes, then you can have a transmitter signal that goes to the antenna, reflects and arrives at the receiver, degrading the isolation. So any circulator is only as good as the matching at the antenna port. But we added these tuning capacitors that essentially create a feed-forward current that cancels the reflected signal at the antenna, so it allows you to maintain isolation even if the antenna impedance changes. And this essentially means that this is a circulator and an antenna tuner all rolled into one. And we're able to tune for as high as almost VSWR of approximately 2 in this tuning circuitry built in. Another new generation of these circulators was this work that was just reported at the ISSCC conference that concluded in February of this year, where we looked into how we can scale these circulators to even higher frequencies, higher millimeter waves. So we went up to 60 gigahertz. And the way that we did this is that instead of using transmission lines between the switches, we actually used band pass filters. And the advantage of a band pass filter is that it allows us to resonate out some of the device capacitance associated with those switches, thus allowing us to push those switches up to even higher frequencies. And so we were able to show a circulator now up at 60 gigahertz in the same 45 nanometer SOI CMOS process with the same roughly 3 dB of loss and with isolation greater than 40 dB over 1.3 gigahertz bandwidth around the 60 gigahertz operating frequency. Aside from these higher performance circulators that both handle higher power as well as go to higher frequencies, we've been working on how these circulators can be embedded within larger systems. So the big benefit of a circulator that's integrated in CMOS is now you can put it on the same chip as the rest of the transceiver and explore co-design opportunities between the circulator and the transceiver. So in a first work, we integrated this NPAT filter-based circulator along with a full-duplex receiver that featured additional self-interference cancellation between the transmitter and the receiver in the analog baseband. But then as we did this, we realized that there's even more co-design opportunities possible. So this was that first chip, and again, you can take a look at the papers to see the performance and see what we were able to achieve. But as we did this first work, we realized that if I look at the NPAT filter circulator, then you have this switch capacitor switch circuit, and these switches are being clocked at the operating frequency. So these switches are nothing but mixers. And you can think of these capacitors as the low-pass filters that would follow a mixer in a receiver. So if I actually look at the voltage across these capacitors, then I actually have the received signal down converted to baseband on those capacitors. So essentially, this circulator embeds the down conversion mixer of a receiver in it, which means that I can throw the low noise amplifier and the mixer that I would normally have in the receiver that follows the circulator away, and I can just take the baseband signals from these capacitors out. So it was a combined circulator and receiver all rolled into one. And because we're eliminating the mixer and the LNA, a lot of performance metrics got better by doing this. So the power consumption was lowered, the noise figure got better, and the transmitter power handling also improved. And we've taken this circulator receiver subsequently quite far, actually. So we've built a phased array with multiple of these circulator receivers on the same chip, 4 of them actually, so a 4-element beam-forming circulator receiver array, where those baseband signals are now combined to give you phased array beam-forming. And what we demonstrated is a full duplex system where not only does the circulator provide you with some initial isolation, but the beam-forming can be used to further suppress the transmitter interference at the receiver to get additional self-interference cancellation. And so we integrated this 4-element full duplex circulator receiver chip with antennas and actually showed full duplex operation in the field using this circulator receiver array. We've also gone beyond phased arrays and beamforming to MIMO. And so in MIMO, you have multiple of these circulator receivers on the same chip, but now they are handling independent and transmitter waveforms, independent and orthogonal transmitter waveforms. So the challenge now with operating a full duplex system in MIMO configuration like this is that from every transmitter to every other receiver, you will now have self-interference, and so each of these self-interferences has to be separately canceled. And so if you have n transceivers operating in MIMO, you have n squared cancellations that need to be performed, and so there's an n squared increase in the power and area complexity associated with those cancellations. So we actually implemented a MIMO receiver using these circulator receiver arrays with this baseband cancellation, essentially sharing some of the delay resources of the canceller across the different cancellers so that the complexity of the canceller only scaled as order of n rather than order of n squared. So again, I'm going fairly quickly through some of these works, mostly because this is a talk that's more focused on non-reciprocity and circulators rather than some of these system aspects of full duplex, both in a phased array and a MIMO setting. But again, I encourage you folks to either get in touch with me or to read these papers to understand how these circulators are helping realize these more complex full duplex transceivers. This particular full duplex MIMO transceiver with the circulator receiver array was reported again at the recent ISSCC conference that concluded in February of this year, just about a month ago. So in this particular work, a 65-nanometer CMOS IC was implemented and integrated 2 of these circulator receivers on there to be able to do 2x2 MIMO. We were able to show plus 14 dBm of transmitter power handling, and we were able to show suppression of one-zone self-interference by 45 dB and suppression of the crosstalk self-interference between the elements by as much as 53 dB across a 20 megahertz operating band. So that sort of brings me towards the end of this presentation. So let me essentially conclude with some remarks regarding future directions. So essentially, hopefully what I've shown is that there's a lot of active research on achieving non-reciprocity through spatiotemporal modulation of material parameters. And this is a field that spans many different physical domains, including optics, electronics, which I've spoken about, but also there's work going on in MEMS and acoustics. And across these different physical domains, the work also spans many different spectral regions. I've shown work at RF and millimeter wave, but certainly in the field of optics, there's work going on trying to achieve non-reciprocity at terahertz frequencies and at true optical frequencies. Hopefully what I've shown today is that specifically when one looks at RF and millimeter wave and when one is focused on IC implementations, then conductivity is a much better parameter to modulate than permittivity. switches are much better devices to modulate than varactors, and these switched capacitor and switched transmission line architectures have enabled the first circulators on chip that now over time have actually scaled to approach the performance metrics that are required by practical applications. For instance, we have shown watt level operation at RF frequencies using these switch transmission line circulators. So what are some of the techniques, what are some of the ideas that we're exploring for the future? So essentially, one aspect about these circulators is they do use a clock, they do use a modulation signal, and so understanding the impact of the phase noise of that modulation signal is quite important. Turns out that the phase noise of the modulation signal can actually mix with the transmitter signal to create a reciprocal mixing-like effect, which is traditionally seen in wireless receivers, and that can degrade the noise performance. So we're actively working to understand this effect theoretically, as well as to come up with means of mitigating this effect. Secondly, we've been able to reach watt-level power handling, but certainly there's an interest in getting to power levels of even tens of watts to be truly competitive with magnetic or ferrite circulators. And so to that end, we're actually looking at using more advanced or more exotic device technologies such as gallium nitride, which have a superior Johnson limit and a superior power handling to CMOS technologies. And so we're looking at heterogeneous GaN CMOS circulators where the switch devices or the power devices would be in gallium nitride, and the controlling clock circuitry, which requires, of course, some digital intelligence, would be integrated in CMOS. And so we're looking at these GaN CMOS circulators to approach another order of magnitude improvement in the power handling of these circulators. So that brings me to the end of the presentation, and I hope you enjoyed it, and I'm happy to take any questions that you might have at this time.
Great. Thank you, Harish. That was your group's doing a lot of really interesting work here. Definitely an interesting subject. So now it is time for a question and answer session. Before we start that, though, remember that you can still submit questions. We've got a little bit of time here to answer those questions, and do that through the Q&A panel in your window. So we'll jump right on into the questions here. There's actually quite a few interesting ones. So is the phase shift between the clock signals realized on chip?
Yes, it is. So that's one of the benefits of building these CMOS circulators, which is all the clock generation is done on chip. So we come in with one external clock, but then we take that external clock, we achieve the phase shift, which is typically done by dividing the clock down. And if you have a differential input clock, then when you divide the frequency by 2, the 180 degrees differential phase shift gives you access to 90 degrees phase shift. So we typically have a divider that divides the frequency down by 2, which helps generate the 90-degree phase shift. And then we have buffering and so forth to get good square waves that eventually drive the switches in the circulator. And again, because it's CMOS and because we can put a lot of digital logic on the chip, we have circuitry to even calibrate the phase shift in case the phase shift isn't perfectly 90 degrees, and we can adjust it to get very precise phase shifts that minimize the loss and maximize the isolation.
Okay, great. So there are a couple questions here on what this does in terms of impedance requirements for the source. Can you make any comments about that? So how do you handle impedance issues and matching structures?
Yeah, right. So on the antenna side, as I mentioned, any circulator is only as good as the antenna impedance that it is terminated with. So you can have great isolation, 60 dB, as high as you want when you're terminated with 50 ohms. But the moment the antenna impedance changes, the isolation will become equal to the return loss of the antenna, essentially. So, it's practically very hard to get anything better than 15 to 20 dB on an antenna's return loss. And so, from my perspective, just the raw isolation of the circulator, getting something way higher than that is actually pretty pointless. And so all circulators have to be followed with an antenna tuner. But what we've been working on is how we can embed the functionality of that antenna tuner within the circulator. And so if I go back here to this chart, so essentially, these switched capacitor circuits that are in the circuit diagram on the left-hand side are essentially compensating for a mismatch in the antenna impedance, and they allow you to maintain high isolation at the receiver port even if the antenna impedance changes. And in this first work, we were able to cover an antenna viswar of around 2. In some more recent works that are unpublished at this time, and hence they aren't a part of this presentation, we've been targeting even higher viswars than that.
Okay, great. Let's see. What about isolation for the on-chip circulators? Can you comment on any challenges associated with that?
Right. So again, isolation. All right. So I think maybe this question comes from the fact that when you're on chip, there might be other leakage paths between the transmitter and the receiver that might limit the isolation. So generally, I mean, I think, in terms of CMOS circuit design, over time, the community has figured out good ways to, isolate different nodes of a circuit or different wires within the layout. And so, we use best practices there where if you want two things to be isolated, make them as orthogonal as they can to each other, use ground shields everywhere as much as possible. Here, this is an SOI CMOS process where most of these circulator works, and so the lack of a conducting substrate helps somewhat as well. But it is definitely true that at the end of the day, on-chip isolation or parasitic leakage paths through ground planes or substrate and so forth have to be considered. Again, any tuning circuit that you have helps because essentially these tuning circuits are canceling the leakage however it may arise, whether it's arising from a reflection at the antenna or through some parasitic leakage mechanism. So we've typically, it hasn't been a challenge to achieve more, especially in these circulators with these tuning circuits inbuilt. We regularly achieve, more than 40 dB of isolation over roughly 20% fractional bandwidth.
Okay, and then I think along the same lines, there's a question here about what the noise penalty is for using the active devices.
Right.
Can you comment on the noise as well?
Yeah, that's a good question. So one thing I would clarify is that these are not active devices. These are passive. So these are passive transistor switches, meaning they have no bias current. Of course, there's a clock signal that is basically driving them, but they are passive switches. They have no power gain. They have no bias current. And so their noise is just the thermal noise of the resistance of these switches. And so these circulators typically have around these RF circulators typically have around 2 dB of loss, and so the noise figure when we measure it is also equal to 2 dB, consistent with a passive circuit whose noise should be equal to the loss of the circuit. That being said, as I mentioned, I think in my last slide, the one mechanism that can still contribute to noise is the phase noise of the clocks, right? So the phase noise of the clocks can degrade the noise figure, particularly when it mixes with a powerful transmitter signal, which is essentially, a reciprocal mixing-like mechanism. And this is something that we have observed in the design, and we're actually actively working on both a theoretical formulation to understand that, which is actually almost done and should hopefully be submitted for publication soon, but also circuit techniques to mitigate that. And so just to give you a sense of what the insight is, it turns out that as long as the phase noise is highly correlated between the switches on the left and the switches on the right, then that phase noise effect cancels and doesn't degrade noise figure. But the moment you have a lot of uncorrelated phase noise between the left side and the right-hand side, then you essentially will have a noise figure degradation. And so the techniques to mitigate this effect involve trying to keep the clock path as common and hence as correlated as possible up to the very end when you drive those switches.
Okay, so actually just to follow up with that question, so in the same way that this is non-reciprocal, do you end up with a case where the noise actually could be like doubly worse because it's through one path you're in phase and in another path you're out of phase, or does that actually help you in some cases?
So there is no doubling of noise theoretically from arising from the non-reciprocity. So in the antenna to receiver path, there's a certain loss, and the noise figure is equal to that loss. But there is some interesting non-reciprocity in the noise behavior, which I sort of didn't mention in detail. So let me actually find that slide. So what we found is that the circulator receiver structure, where we're tapping the baseband signals from the capacitor and taking the signal out. When we were trying to analyze the noise figure of this, obviously the antenna source noise arrives at the receiver. That's straightforward. But we were trying to analyze the noise because of the resistance of these switches, just the thermal noise of these switches, and to see what happens. And it turns out that this noise also experiences the non-reciprocity of the circulator, where the noise on the left-hand side, that noise can only circulate in one direction. And so the noise on the left-hand side, what's marked in green here, has to circulate away from the receiver because only clockwise propagation is supported. And so that noise circulates clockwise and dumps itself in the transmitter termination, while the noise of these switches here on the right-hand side, traveling clockwise, will actually appear on these capacitors and will be sensed by these baseband amplifiers. So noise also circulates just like signal does in the ring, which one would expect.
Okay. All right. Yeah, sure. That answers that. Okay, let's see here. Any comment on the maximum power handling capacity or impact on that from these circuit configurations?
Right. So the best that we have achieved so far is in this RF circulator work. So I think that the frequency isn't mentioned on this slide, but the circulator it works at 1 gigahertz, and it has a transmitter to antenna P1dB of around a watt, so 30 point something dBm, and the transmitter to antenna IAP3 is about 50 dBm. And so given that typically in these things you want to be backed off from P1dB, you can put probably several hundreds of milliwatts, close to a watt of transmitter power into the transmitter port of this circulator. We have a follow-up on this work, which I didn't present today because it's not yet published, also supported by the DARPA SPAR program. So, it has been presented in that program to the sponsors, where, we've made some further enhancements on this idea and taken the power handling up to around 4 watts. Or at least a transmitter to antenna P1dB to around 4 watts. So that's sort of where we're at. I think at this point we are more or less at the limits of what a straight-up SOI CMOS process can do. I think in the 1 to 10 watts range is where we're sort of maxing out at for SOI CMOS. But to get beyond that, to get into the tens of watts, we're looking at gallium nitride technologies. So that's what I mentioned as one of these future work topics here.
Sure. Okay. Yeah, that sounds good. And I guess along the same lines, what are some of the remaining limitations for pushing the performance of these? Is it parasitics? Is it materials? Is it the CMOS technology?
So on the power handling, it is certainly at this point. I mean, I think. I guess you never want to say that there's no architectural advance that's left to be had, right? Because, there's always new ideas. So, I don't want to shut the door to new ideas that, might be made on this architecture here that give us even more power handling in CMOS. I guess it's not impossible, but at least we don't have anything new beyond the 4-watt work, which at least isn't reported yet in these slides and hopefully will be published soon. So I think, getting to higher power handlings in the tens of watts is largely a technology issue at this point. Gallium nitride will help. I think there are some other open questions still. The phase noise question is something that I mentioned. I think, we have a handle on it, but it's something that we have to demonstrate experimentally that even in the presence of a powerful transmitter signal, the phase noise of the clock will not degrade performance. That's one open problem. The other open question, I think, is so when you have perfect clocks that are exactly 0 and 90 degrees, then you have no spurious emissions. But if there are some small timing mismatches, then you will see some leakage of the clock signal to the antenna and some cross-modulation terms between the transmitter signal and the clock that appear at the antenna. So there are some spurs that you will see. These typically tend to be out of band spurs, and so they can be filtered with an additional filter following the antenna, but ways to, even within the circulator, calibrate the phases accurately so that these spurs are inherently suppressed, I think, is an interesting topic, so that you don't have to add filtering and, take the associated loss hit with that filtering. And so spur mitigation is something that we're looking at, which, any clock circuit is going to have some spurs associated with the clock, but these are things that, in the circuits community, work has been done to, to calibrate those out.
Okay, great. We probably should have asked this earlier, but any comments on comparing these to kind of traditional circulators and related systems?
Yeah, so I think when you look at the traditional magnetic circulators, if you want to perform an apples-to-apples comparison, one is obviously the power handling is probably still an order of magnitude away. The best we've done is a few watts, while commercial magnetic circulators can easily achieve tens of watts. We're trying to bridge that gap with gallium nitride, and I think initial results show that there's promise there. Of course, these circulators do consume power, while magnetic circulators, aside from the biasing magnetic field, are completely passive. And so the power consumption in the clock circuitry has to be factored in. In some of our recent work, such as the one that's on the slide that's being shown here right now, that power consumption is negligibly small compared to, for instance, the power amplifier that's generating the watt of power that goes into the transmitter port. And so I think we've been able to show that the power consumption should be negligible in a system context. I think the way that these circulators will really shine compared to the magnetic circulators is in all the benefits of bringing them on the same chip. So a reduction in size, a reduction in weight, also co-design opportunities between the circulator and the rest of the system. So, for instance, you can embed the antenna tuning, so you don't need a separate antenna tuner after the circulator. So I think those are really, the goal is to exploit those benefits in a system context while not taking too severe a hit in things like power consumption and so forth. Power consumption, power handling, etc.
Yeah, I see what you're saying, but you mentioned the key word, which is apples to apples. So when you're just comparing insertion loss, it's kind of not exactly a fair comparison, right? Right.
I mean, and if you just compared insertion loss, to be fair, we would be worse off right now, because we're typically in the 2 dB range, and ferrite circulators can be as low as half a dB. But you really should compare this to a circulator plus an antenna tuner. And so then a ferrite circulator plus an antenna tuner is probably, 1 to 1.5 dB or thereabouts. We are working on things that are trying to lower the loss of our circulators to approach 1 dB. This is a fully integrated circulator, everything in CMOS. A lot of the loss comes from these passive components. You see a bunch of spiral inductors here on this die. A lot of those spiral inductors, you can use technologies like integrated passive devices, some extra back end of the line thick metal layers above the chip. There are ways to lower, the loss of those, right? So I think, it's a relatively new field. I mean, we've been working very actively on it, but if you think about the first circulator that we demonstrated, it was almost just 3 years ago. So it's only been 3 years that we've been hammering away at this. So, I think we're definitely trying to bridge the gap in performance, but offer functionalities that are uniquely enabled by having these circulators on chip.
Excellent. Yeah, this has been great. Thank you for answering all of these questions. We are really close to being out of time here. There are multiple other questions that we'll get the presenter to follow up with these unanswered questions offline. So as stated earlier, this session will be archived on the Society website at mtt.org. So please visit and explore the new, updated, and stylish MTT website where you will find these webinars. Also, registrants will also get an email reminder with a website address when that's available. For attendees who would like to receive PDH credits, let me go to that slide here real quick. Yeah, this slide that's shown right now, there's a code there on this last slide of the presentation that you can use for those PDH credits. Once again, I'd like to thank Professor Krishnaswamy for this excellent and informative presentation. Special thanks to our audience today for joining us. We hope you found today's event valuable and that you'll return for future IEEE Microwave Theory and Techniques Society webcasts. Thank you, and have a great day.
Thank you very much.